Optical scan technology, which is also sometimes called optical mark sense technology, was first developed around the 1950s, and it was originally used for scoring standardized tests. Anyone who's taken the SAT has used one of these systems probably. It's if you filled out one of those bubble forms with a number 2 pencil, that's optical scan. Optical scan voting was an idea that came along around the 1960s. People developed the first initial machines based on the testing technology, and then gradually these machines became deployed and very widespread in the US. If you think about the paper ballot from the 19th century that you put in a ballot box, one of the biggest problems with it was the integrity of the counting process. If malicious insiders took over the counting process, they could announce whatever totals they wanted. So the idea with optical scan was to replace these potentially malicious, certainly subjective humans who were part of the counting process with an impartial, automated machine. So we move from that 19th century technology of the ballot box to the 20th and 21st century technology of the precinct count optical scanner. So let me illustrate the way the voting process works with one of these machines. The voter fills out their ballot and puts it into a slot on the machine. At that point, the ballot goes into a ballot box that's attached directly to the scanner. At the end of the election, after everyone's voted, the machine prints out a paper tape that has the totals for how many bubbles were filled out for each of the candidates. Most of these machines also have a removable memory card, a storage card like the flash memory for your digital camera, and this maintains an electronic record that should match the paper tape. So here are a couple of styles of ballots for use with optical mark sense or optical scan voting. On the left, this is a very common style. You see there are these broken arrows, and the voter just has to fill in the gap between the arrow for the candidate they want to select. Another style is much more similar to the SAT, standardized tests. They're little ovals that the voter fills out. Here's what's happening inside one of those machines. So this is a technical illustration from a patent, but we can demystify that a little bit. What you see there on the left side of the screen is a light source. This is going to illuminate the ballot as it moves by. Then in the middle, you have an optical sensor. Basically, this is the machine's vision system. It's able to see the bubble, and the ballot flies by underneath. So what actually happens inside one of these machines is a little bit more sophisticated and turns out to have some important implications for the voting process. So inside the machine are an array of emitter detector packages. Each of these is basically a light source coupled with a very simple kind of light detector. As you can see here, there are 8 of them arranged in columns in a line under which the ballot will pass. So the ballot in this picture is moving from the bottom to the top underneath these sensors 1 through 8. And each of these sensors is going to produce a different amount of electrical current depending on how much light it senses. So if there's a mark on the ballot underneath the sensor, that will register differently from a space that's not marked. On the left and right of this ballot, you see these rectangular marks, and these are alignment marks. These tell the scanner when a row of ovals is going to be passing under each of the detectors. And these detectors are like very, very simple kinds of eyes. All they can do is sense brightness or darkness. You can imagine that if you were to hold up a translucent piece of glass in front of your face, you could tell whether it was daytime or nighttime, but you couldn't see much else. This is all the sensitivity that each of these has. Inside the machine's electronics, there's some preset threshold that separates an area that's considered to be dark enough to be filled in from an area that is light enough to be not filled in. But exactly where to set this threshold is a tricky thing to determine. Conceptually, what this results in is that there are a grid of locations on the ballot page where the scanner could detect a mark. And this has implications for the layout of the ballot and for the positioning of those alignment marks, as you see here. A more modern style of optical scan machine uses a more sophisticated detector that's a bit more like what you'd have in a fax machine or a computer scanner. This kind of array, instead of having just one sensor per column, has many sensors per column, and it produces an output that's much more similar to the kind of picture you might take with your digital camera. This has possible positive implications in that it can capture much more information from the ballot and be used to distinguish marks with greater accuracy. On the other hand, in order to go from a picture of part of the ballot to knowledge about whether it's marked or not, requires some pretty fancy computer algorithms. So this has to be implemented in software. There are two styles of optical scan machines that are really commonly used in voting. And one of these is the one I mentioned at the beginning of this segment, the precinct count optical scan machine. And you see one of those on the left. This is one that is in the precinct. The voter inserts their ballot right there, and it goes into a ballot box directly. The other kind of optical scanner is something called a central count optical scanner. And this involves collecting the voters' ballots at the polling place in a more traditional kind of ballot box, and then transporting them to a central location and feeding them through a high-speed scanner in bulk. The advantages of precinct count include that you're making a record of the voter's vote immediately, so there isn't a risk that the ballot box, there isn't as much of a risk anyway, that the ballots might be tampered with before they get to a central counting location. Probably the biggest advantage, though, is that a precinct count optical scan machine can look for problems with the ballot. It can see that the voter has made too many marks for one candidate or has forgotten to fill out something potentially, and send the ballot back to the voter to try again. This really helps cut down, especially on the number of overvotes, on instances where the voters mark too many choices. So it's a really important kind of usability feature. Central count machines can't do this because they're not interacting directly with the voter, but they do have the advantage that you need a lot less equipment. You can do a central count with just a normal ballot box at each precinct. You don't have to own and maintain and store a fancy computer voting machine for each polling place location. So now you have some sense of how optical scan balloting works. I'd like you to take a minute and think about what could go wrong. So there's a lot that can go wrong with optical scan voting, just like the other kinds of voting we've discussed. One of the more prominent issues has to do with the way people interact with optical scan ballots. So ballots generally provide some instructions for how to fill them out. For instance, use only a number 2 pencil, completely fill in the oval, etc. If you give directions like these to people, how well do you think they're going to follow them? The answer is that not everyone follows them exactly right. Here's a collection of marks from real voted ballots in one particular election. You can see how much variation there is here. Some people used blue ink, some people marked an X instead of filling in the oval. At least one person used red ink, and each pencil mark is slightly different. So this is a challenge for optical scan machines because it's possible that the machines are not going to interpret every one of these marks as a valid vote. Now here are some of the problems. One issue is that these simple emitter detector sensors, the ones that can only sense brightness, respond differently to different colors of marks. They're going to be more sensitive to certain parts of the visible spectrum than others. So certain things that might look very dark to the voter, to a human, might not look like they're marked very darkly at all to the machine. In particular, certain kinds of sensors that are very sensitive to infrared might not see red as a mark on the ballot at all. It might not be able to distinguish between red or white. Another kind of problem is that the older style of optical scanner that uses these sensors that essentially form a grid of potential target locations are very sensitive to the alignment of the ballot. So if the ballot slightly changes size because it's a very humid or a very dry day, these cause paper to expand or contract, some of those bubble targets aren't going to be perfectly underneath the physical locations of the sensors anymore, and they might be read less well. Another problem is the directional alignment on the page. If the ballot's inserted into the machine slightly crooked, as you can see in this illustration, that's another case where the sensors might not be perfectly over the targets. Another issue is calibration. Each of those sensors in the machines might respond slightly differently to the same intensity of light because of physical variations in the electronics. So calibrating them, making sure they're all responding appropriately is a really tricky maintenance task. And then there are different kinds of marks. As you see here, certain kinds of marks that are not completely filling in the oval might not be detected when compounded with other factors, like a slightly crooked ballot, or they might sometimes be detected and sometimes not. It seems that because of all of these factors compounded, an optical scan ballot has some chance of having errors in the scanning process. And in an election of any size, you're almost certainly going to have some fraction of ballots and some fraction of votes that are misread or lost because of problems like these. This is fundamentally a challenge to almost every voting system, though. We don't yet know how to make a voting system that will work on a very large scale with absolutely zero error. The problem with optical scan, though, is there are a lot of different and somewhat tricky errors like these that could potentially add up to a problem, especially in a very, very tight race. So it's important to do things to make sure voters fill out the instructions correctly. We'll talk a bit about that in a later lecture when we discuss usability issues. Another kind of problem with optical scan is something that some colleagues of mine from Princeton pointed out in a paper just a couple of years ago. And that is that they looked at the styles of ways that different people fill out those little circles, those ovals, on an optical scan form. And they found that different people had a distinct enough style, all of these different ways of filling it out, that you could actually identify two marks that came from the same person. So this is a somewhat theoretical attack today, but in the long run you do worry that these small differences in how people fill out these forms might be something that could be used to compromise voter privacy. There's one more category of problems with optical scan, and perhaps this is what you thought of when we asked what could go wrong. And that has to do with the fact that these machines are counting votes by computer. So if you think about how these machines work, the parts we've talked about so far are mostly the electronic parts, the actual scanning apparatus. But also inside the optical scan machine is a computer that's responsible for reading the signals from the scanner, figuring out which candidate should receive the votes, and maintaining totals, running totals of the number of votes for each candidate. This is the equivalent of those gears and counters inside the lever machine. But unlike gears and counters, all of this in an optical scan voting machine is controlled by computer software. And computer software can be changed. It can be changed in ways that are invisible. We'll talk much more about that kind of problem later in this and the next lecture. But first, I wanted to give you an example of a demonstration of a way a computer voting machine could be used to cheat. And this is an attack that was conceived and demonstrated by a voting researcher named Harry Hursty about 5 years ago. Harry Hursty's attack was against an optical scan voting machine made by Diebold. And Harry's attack looked at what would happen if the criminal, an attacker, had access to that memory card, the card that's used to hold an electronic copy of the results and take it back to the central office for counting. So let's assume that the card is going to be very well protected after the voting process finishes. Because after the voting process, everyone knows their votes stored on it. This is an important part of election integrity. But what if someone was able to get access to the card before all of those votes were cast, when maybe people aren't realizing that it has important security properties? So Hursty's attack works like this. Before the election, he's going to try to do the electronic equivalent of stuffing the ballot box. He's going to load up the memory card with a number of votes for the candidate he wants to win. Let's say it's Ben. At the end of the election, this is going to be 10 votes added to the total for Ben, because each time someone else votes, the voting machine is just going to increment. It's going to count up on that number. Now, the problem with this very simple version, just let's say we add 10 to Ben's category at the beginning by just putting the memory card into a computer and changing the file, something like that. The problem with this simple version of the attack is that it would be pretty easy to detect. All that the election officials would need to do is observe that the total number of votes in the machine is 10 more than the number of people who used it. So that would be caught right away. So Hursty kept thinking and looked for a way that he could make the total number of votes match the number of voters while still moving votes from one candidate to another. What he realized was that the voting machine's record of how many votes belong to each candidate performs arithmetic in a very similar way to one of these mechanical counters. Think about the odometer on your car. Maybe your odometer has 6 digits, and in that case, after you get to 999,999 miles and drive one more mile, your odometer is going to wrap around back to 0. The memory card in the voting machine worked in essentially an identical way. And Hursty realized that if he programmed 10 votes for the candidate he wanted to win and, say, 990 votes for the other candidate, then when real voters used the machine, both numbers would increase. Let's say everyone is going to vote for George. He's going to get at least 10 votes. And it's going to wrap around back to 0. So here we've had 10 votes for George, 0 for Ben, but notice the total still adds up. A total of 10 votes are in the machine. That's because the votes for each candidate, the added votes for Ben were canceled out by that initial 990 votes for George and the wraparound effect. A slightly simpler way to think about this would be to think about that 990 votes as being equivalent to negative 10 votes for George. In the way computers represent numbers like this, those two are almost equivalent. So here you see the first example of a computer-based attack on a voting system. Luckily, because these are optical scan ballots, we have a way to catch this kind of fraud, which is to actually look at the paper ballots in the ballot box. But more about that later. First, I want to talk about computer voting machines that don't have that kind of paper backup. And those are DRE voting machines, the subject of the next segment.